Okay, I'm going to use slides I've already written on because I recorded this lecture and it disappeared. So here we go again. So I'm using the same slides that I recorded earlier, guys. Probably going to take you some pausing for them. Electrochemistry. First, we're going to do a redo of redox, right? Let's talk about redox. From Chem 1, oxidation, reduction. You'll remember the acronym like LEO-GR or oil rig, where LEO means lose electrons, oxidize. Oil is oxidation, is the loss. And then GR, let's see, gain electrons, reduce, or reduction is the gain for rig. And in oxidation and reduction, whatever's being oxidized is known as the reducing agent, and whatever's being reduced is known as the oxidizing agent, because the reducing agent helps something get reduced and the oxidizing agent helps something get oxidized. The charge of things is called an oxidation number when we're doing redox reactions. Now, let's see how we can... You remember in Chem 1, we did a copper cycle lab. I hope some of you guys that took chemistry elsewhere might have done a copper cycle lab. And in the copper cycle lab, we started with a beaker that had a blue solution in it, and you'll remember that a blue solution is indicative of there being copper ions in the solution. And we started this lab with a piece of copper wire, and you put nitric acid on it, and it gave off a brown gas. So many of you are probably familiar with doing that lab. And then towards the end, we measured out some little granules of zinc, and we put them in the beaker. And this is the reaction that happened. And when we put the granules of zinc in the beaker, the color of the blue faded away. Because see, the blue was there because there were copper ions in solution. Those copper ions gained electrons and turned into just solid copper. And that's what you see showing up now in my beaker. I did little red dots. And in the lab, it was like a reddish brown copper. And so the gray zinc, this started out gray that we put in there, it seemed to disappear in the beaker, but it didn't really disappear. What happened is it was oxidized. The zinc was still in there, but all the little gray zinc, each atom of it lost 2 electrons, and so the zinc ions were in solution. You couldn't see them, but the zinc was still there. If we take this reaction and we split it into what are called half reactions, it would look like this, that the copper 2 is turning into copper and the zinc is turning into zinc 2. These half reactions show it's splitting up what is reduced and what is oxidized. Okay, we want to balance these half reactions in terms of their charges. And the way you do that is by putting electrons on them somewhere. So if you look at that first equation, we can see right here there's a +2. And on this side, that's elemental copper. What is the oxidation number for anything in its elemental state? It's 0. All elements are 0. So in order to balance these charges, where you've got a +2 here and a 0 here, again, you're balancing with electrons, which have a negative charge. So see, we're going to add 2 electrons to the reactant side. That gives this side 2 negative plus 2, overall 0 charge. And now that matches this side. Okay, and that's 1/2 cell. That represents a half cell. So how would you balance the zinc reaction with electrons? You would put 2 electrons on the product side. And I should point out that what I have written in black here, this is the net ionic equation, okay? The actual equation was this that is showing up in purple. Because that blue solution that started out in that beaker, the blue liquid that had the copper 2, it was really copper 2 sulfate, okay? And what I did is when I showed you what was going on here and we broke into half reactions, is I had eliminated those sulfate ions because those are spectator ions. And typically when you're looking at these electrochemistry reactions, what you're presented with at the start is the net ionic equation. Typically, the spectator ions have been removed. Now, what we're going to be looking at in electrochemistry is what we did in Chem 1, we had all this in a beaker, okay? We had a blue solution of copper in a beaker, and we put zinc in it. In electrochemistry, you actually split this up. So you have your beaker of copper sulfate, which is a blue solution. You put a piece of copper metal in that beaker. And then on the other side, you have a zinc solution, zinc sulfate, or zinc nitrate or whatever, and you put a zinc electrode in that solution. We connect these electrodes with a wire. Typically there's a voltmeter in the middle, and electrons are going to flow through that wire and generate a voltage. So unlike Chem 1, where it all happened in one beaker, that's great. To make a battery, you split these up. And each of this whole system makes a cell, a galvanic cell. But what you do is you take each half cell reaction and put it in a different beaker. Okay, going through section 19.1 of your book, that's where we are here, we just balanced a simple half cell reaction, okay, because that one was easy to balance, to take the, to split up the copper reaction and add the electrons, and the zinc reaction and add electrons. But it's very common, I'm sorry y'all, I know it's jumping back and forth. It's because, like I said, I recorded the lecture, and when I went to upload it to YouTube, it was 4 seconds long. And as you can see, I'm talking way longer than 4 seconds. And so I decided I would just go back through and talk over the slides I had already written. So that's what I'm trying to do. Section 19.1, I'm going to balance this equation that you have written. It's the same one your book does, okay? And it talks through the steps in the book, but I'm gonna walk you through the steps here, but you can reference it in your book. The first thing you do is separate the half reactions, okay? So I'm kind of started doing the iron one there, but just like you did the copper and the zinc, y'all can probably do this, like pause the video and separate these half reactions, just like we did with the copper and zinc. So just try it. And then when you start back up, I'll show you what I was asking you to do. Okay, that's the half reactions separated. And obviously this one's a little bit more complex because it's not just iron and chromium. There's some oxygens in that chromium. So we're going to talk about how we do that in a minute. Okay, the first step in balancing these is to balance all the atoms besides the oxygen or the hydrogen. Okay, so in this one, iron is balanced. See, iron, iron, that's fine. But there's 2 chromiums here. So first we balance the chromiums by putting a 2 over here. The third step is to balance the oxygens with water. So there's 7 oxygens here. That means we're going to add 7 waters on the product side. Now, in balancing the oxygens with water, we also introduce hydrogens to the equation. So the fourth step, we have to balance those hydrogens. And we're going to balance them using H pluses. So how many hydrogens are here? There's a total of 14. So that means on the other side, on the reactant side, we're going to need 14 H's, 14 hydrogen ions, 14 protons. Okay, now the fifth thing we have to do is to balance the charges with electrons. We did this on the other slide, you know, with the copper and the copper 2, and the zinc and the zinc 2. Okay, so look at the iron. You have a +2 and a +3. You can only add electrons to one side, okay? So we're not making both sides be 0. We're making them match. So you're always going to add the electrons to the side that has the higher charge. So since this side has a +3, to make it match the reactant side, we're going to add 1 electron. Now the next one's a little bit not quite as easy to balance because you got to be careful in counting your charges. So look, +14 -2, that gives you a +12. This is +6, this is 0, that gives you a +6. So always add to the higher charge side. Obviously we're going to have to add to this side, and to make those balance, we're going to add 6 electrons. Okay, the 6th step is you have to balance the electrons. Okay, that went a little further than I intended to go. Forget those parentheses, they're not there yet. So look, at this point, when we did the copper zinc, if you look back at that, we ended up with 2 electrons on the product of one and 2 on the reactant of the other. But in this one, you can't have this one producing 1 electron and this one needing 6. Those numbers have to match. So to make those match, we're going to multiply the top equation by 6. And let me explain again a different way of looking at it. If we had this, that X yields Y, and that's 2 electrons, and M yields N, and that's 3 electrons, okay, say these had balanced like this. Then to make the 2 and the 3, so they got to be the same number. We would end up multiplying that top one by 3 and the bottom one by 2. That's what we would have done in that case, okay? Does that make sense, I hope? Of course, y'all are going to practice some, but now, when we multiply the top one by 6, we distribute that out. So see, it changes the iron 2 to 6, the iron 3 to 6, and the electrons to 6. And at this point, see, now the electrons cancel. What's being produced in the first one is being used in the second one. And so this is what our overall equation looks like. Okay, now this is an example of balancing one in acidic solution. Okay, so this one's finished because that would have been an acidic balance. Sometimes you're given these problems and it says balance it in a basic solution. So that adds some steps. So if it were a basic solution, there'd be another step. For every hydrogen ion, you would have to add hydroxides. So this is only going to affect, in this one, it's only going to affect the dichromate one. Look, there's 14 H's there. That means you would add to that side 14 hydroxides. Okay? If we add 14 hydroxides there, we have to go and put 14 hydroxides. See, hydroxides are the base. We have to go and put those on the product side as well. Now, over here, if you got 14 hydrogens and 14 hydroxides, those are going to combine as 14 waters. Okay? So then, you would do the next step, you would cancel the waters. So what happens is if you had 14 waters on the reactant side and 7 on the product, all 7 on the product side are gone, and the 14, oh shucks. And the 14 would become 7. Now, to practice this, I want you guys to look at, in your book, sample problem 19.1. I'm just going to put this whole slide up there and then talk it for a second. In my book, it's on page 879 because mine's a 5th edition, so that should match your ebook. But I know a few of y'all have an older edition hard copy you're using, so that it's not going to be on that page, but it's the first sample problem in the chapter, 19.1. 19.1 is a basic solution one. It gives you the problem, and then it works it out step by step. Along with that sample problem underneath, there's a practice problem A and a practice problem B. So you guys practice those. The answers to all the chapter stuff, like these samples and practices, the answers, y'all, are at the end of the chapter, after all the end of chapter problems. Okay? I also want you guys to look at checkpoint 19.1. Okay, that it comes right after this, these samples. There is a connect for these, but the connect for chapter 19 that I posted, there's only 5 questions, I think. Maybe 6, but there's like 5 questions on the connect. So y'all probably need more practice than those 5 questions. So work these within the chapter. Now, let's look at what I was telling you about at the beginning. If we split these up and have the copper going on in one beaker and the zinc going on in another beaker, if we split them up, we can have it's called a galvanic cell. Or that copper-zinc system is specifically known as a Daniell cell. It's named after the man that came up with it, that figured it out. Okay. I'm coming back to that in a minute. That's Salt Bridge. Here. This is a picture in your book of figure 19.1, okay? And so what you see at the bottom here, that's this, what we talked about earlier. If you put zinc in a blue solution of copper, and then you just wait a little bit, see the blue color fades, and y'all can see on this electrode all that little red, brown copper plating out. That's the blue ions in the solution turned into solid copper. They gained electrons. It was reduced. And if you actually were to look at this piece of zinc metal, this one is heavier. This zinc is lighter. Because, see, the zinc was getting oxidized. The zinc metal over here lost 2 electrons. And so that metal, that rod, was getting eaten away. It was corroding into the solution. So what we're going to do for a half cell, we're going to have in the left beaker zinc sulfate with a zinc electrode, and in the right, copper sulfate with a copper electrode. And we're still going to have this reaction happening. Okay, but we're just going to split it up into its half reactions to produce a galvanic cell. The zinc is going to be oxidized, and the copper is going to be reduced. Oxidation always happens at the anode, always. Reduction happens at the cathode. And y'all, the way I keep it straight is, look, oxidation and anode start with vowels. Reduction and cathode start with consonants. So that's easy. Oxidation at the anode, reduction at the cathode. Electrons are going to flow from the anode to the cathode. Okay, they're going to flow through that wire. And when they flow through that wire, depending on the difference in the potentials of the zinc and copper, it's going to produce a voltage. Depends on the system. Y'all, if you look on over in these diagrams, you can see the voltage there at 1.10 volts. And we'll talk more about that in a minute, but let me just finish talking to you about how the cell works. Okay, so what's going to happen as the electrons flow towards the cathode, you get a buildup of positive charge at the anode. See, because electrons are leaving, so the positive builds up. Well, if electrons are flowing to the cathode, what's going to build up over there? You're going to build up a negative charge. Okay? When this charge gets to be really different, when you got the buildup of positive at the anode and the buildup of negative at the cathode, it'll stop working. Okay? You can't have this big charge difference. So that's why we introduce something called a salt bridge. Okay? And now that's where this comes into play. I'm going to jump back a slide. A salt bridge is just an electrolyte. It can be like potassium chloride or sodium chloride or lithium chloride or lithium bromide, whatever. It could be ammonium nitrate. What you want in your salt bridge is you want it to have ions that won't react with anything in your solution. Like in our example, the copper and the sulfate and the zinc. And so typically your salts have like group 1 metals. See, group 1 metals are always soluble, right? They never precipitate anything. Or your salt would have like a nitrate because they're always soluble. Chlorides are good too, as long as you don't have, silver, mercury, lead. Anyway, the salt bridge prevents this buildup of charge differences because the anions of the salt, anions are negative, anions flow towards the anode, okay? And that helps balance out that buildup of positive charge. The cations of the salt flow towards the cathode, and that helps combat the buildup of that negative charge. That's why it's called a cathode, because the cations are flowing there, and the anodes, because the anions are flowing there. Oh, I keep doing that, I know. Okay. So let's talk about where this 1.10 volts comes from. And if you look at the bottom one here, got it circled in yellow, the 0.9 volts. I'll talk about that in a minute. But the 1.10 volts, where do we arrive at that from? That 1.10 volts is called the cell potential, or the cell voltage, or the cell electromotive force. Okay, these terms are used interchangeably. They all mean the same thing. That is calculated. This is how it's symbolized. Cell potential. You'll remember that little degree symbol means standard state conditions. okay? What does that mean, degree symbol? It means like 25 degrees Celsius. It means gases are at 1 atmosphere. It also means for this system that all the concentrations are at 1 molar. So this is why, when we go back to the previous slide, see, it starts out at 1.10 volts. As this reaction proceeds, the concentrations don't maintain 1 molar because you're adding, one side's getting oxidized and one side's getting reduced. So as the concentrations start to get imbalanced, just from this cell working, you start to decrease your voltage, okay? And so that's what that figure's showing. It goes down over time. You don't have as much voltage produced. Now, how the cell potential is calculated, you take the cell potential at the cathode minus the cell potential at the anode. This is the formula. I'll show you where you get the numbers from a table after we introduce the formula. Another way of thinking of this is that the cell potential is equal to the reduction potential minus the oxidation potential, because cathode minus anode is reduction minus oxidation. Okay, now, where do we get the numbers from? There's a figure in your book. This is on page 887 in my book, and it's a table of standard reduction potentials. This is where we get the number from. You want to print this table. You're going to want it handy because this table is how we read in this table is how we answer a lot of questions about electrochemistry, okay? Like in the previous chapter, I told y'all to have that KSP, KA, KB table in chapter 16, 17. Have that handy. So for this one, you're always going to be referencing this table. In the classroom, I would have handed y'all a copy of this as we finished the lecture, okay? And you would have always been referencing this table. So, for the reaction that we're doing, find those two reactions on the table. Now, the table is reduction potentials. So every reaction on the table is a reduction reaction. Now in this one, in the copper zinc, the copper is getting reduced. So on the table, it's going to show up just like that. That reaction is going to say copper 2 going to copper solid. Be sure you pick the right one. There's more than one copper. Now the zinc reaction on the table, because in this reaction, zinc is getting oxidized, but what you're looking for on the table is going to be opposite of what's written. Okay, so one of them, the reduction potential is just like the table. The oxidation potential on the table is going to be opposite. So take a minute, pause it, and find those two on the table. Okay, so here they are. I found the two on the table. Be careful, I think it shows up still. No. I want to point out that there's another copper on the table right here. Don't pick that one, because look, it's copper 2 to copper 1. Okay, it's based on the reaction you're given. So there's a couple of those that happen on the table where there's more than one reduction. Just be sure you're looking up the right one. So here we're talking about, we know it's 1.10 volts because it was shown in that diagram earlier, but let's look at how we know that. All right, the cell potential is at the cathode, which is what's getting reduced, minus the cell potential at the anode, which is what is getting oxidized. On this table, when you find the two, the cathode is always at the top and the anode's always at the bottom. It's always that way. It's how the table's listed. So whatever is showing up at the cathode is above the anode. So to calculate the cell potential, we take the 0.34 volts, and it's hard to see because I wrote anode right over the number we need, but that cell potential, you can see it in your book, is negative 0.76 volts. And so when we do that math, we get 1.10 volts, okay? The cathode minus the anode. And I think at this point, I think I overlap a little with my other video. I'm going to keep going a little bit because I just had all kinds of flub-ups this morning, and I stopped recording when I was talking, and I can't remember where I started. I think right here is about where I stopped, but did I say... On this table, I don't know if it catches it in the next video, so I'm going to tell you here. These cell potentials are intensive properties. You remember, you've got intensive and extensive. Extensive things depend on the amount, okay, like mass. Like the mass of something depends on how much you have, right? The volume of something depends on how much you have. These aren't extensive. These are intensive. What that means is that if when we balance this equation by half reactions, if we have to put a 2 on the coppers, that doesn't change the cell potential. Okay, you don't double it. That also, these are reduction potentials. We use the numbers as is. Even though what's going on in this reaction that I have written here is zinc being oxidized, even though this reaction shows zinc being reduced, we don't go in and change that number. We don't flip the sign, okay? The table is intensive. You take the numbers straight from the table. Okay, from here, I think the next video covers, because the next thing I do on the next video is working something besides the zinc-copper system. Now, I'm going to try to upload this, and hopefully it won't get deleted or I'm not going to be happy. So, again, work the practice problems in the book. The next video is going to have some more practice problems for you because there's a limited number of connect to do. And then we'll probably have one of those conferences, or you guys can email me if you have questions about the problems.